Hey, welcome guys. Yeah, so today let's talk about fundamental theorem of algebra and the proof using analysis. So remember the previous video we just define exponential function and trigonometric function by power series. So today let's go about fundamental theorem of algebra, and I hope you guys subscribe to my channel. Okay. So and there's a video that maybe 1 year ago, and talking about linear theorem and the fundamental theorem algebra. Okay, so let me just and you can check that if you want that proof. Okay, so let me just write down everything I know about. Okay, so yeah, so there's this thing called the fundamental theorem of algebra. I think maybe the first is proved by Gauss or something. Yeah, so basically the idea is that you have a polynomial z, let's say p n z, let's say a n z n up to a0, where n greater or equal to 1 and a n is non-zero. And the theorem says that Pn of z has at least one complex root. Okay, so just saying that there exists a z0 belongs to complex number such that Pn z0 is 0. Okay, and then once you know there is a root, then you can divide your Pn z by z minus z0. And then you keep going, use theorem. So basically, you can easily show that there should be n complex roots. Count multiplicity. Okay. Okay. So as far as I know, there's at least 3 different kinds of proof. Okay. But in this video, we talk about analysis. So one common way is to using a complex analysis, which is basically based on the linear theorem. Says that basically the linear theorem says that bound the entire function. Entire means holomorphic on a complex plane. Bound the entire function is only constant. Is only constant. Okay, so let me just quickly mention the idea. So idea is that you first pick out in large in you just consider f of z to be 1 over pz and assume that there's no roots. So your f of z will be entire. And then you consider radius of r, and you can easily show that you can, when r pick large enough, then the least and all the region larger than r will be bounded, and the f of z is a continuous function on this, right? So in a complex set, you always bounded. Okay, so then you can easily show that this is bounded entire function, so it must be constant. But this guy is a polynomial, so it should not be constant. So contradiction. Okay, and the second proof is using the Galois theory plus a little bit analysis. And this proof analysis, and this proof I will do in the future. So this part is a little bit tricky. So, but I think all you need to know is that Galois C over R is just Z2 Galois group, and also using some analysis and saying that, and you can prove that if there's no roots, then it will contradict this automorphism, this Galois group of this Galois group or C over R. Okay, and the third proof, which is what I'm going to be doing now, is using analysis. Okay, so quickly do this. Okay, so let me just suppose my P of Z to be Z to the N. By the way, I can assume AN to be 1, right? Because otherwise I just divide AN. Okay, and N should be greater or equal to 1. Now let's so the proof goes as follows. So let's let mu to be inf of P of Z. Okay, and the Z to be all complex plane. Okay, so the key analysis, right? So analysis tell you that this inf exists because this absolute value is greater or equal to 0, and we are working in a real number, so this inf always must exist. And I can consider Z as a radius r. And by these results, I can get the P of Z will greater to R to the N minus 1 minus A N minus 1 absolute value R inverse minus 1 and the minus A0 R minus N. Okay. So this just tell you that if you consider radius of R at Z equals R, right? You can control this P of Z. Prove that P of Z will greater than something, right? So that means if you choose R to be large enough, this P of Z can goes to infinity. So this P of Z can goes to infinity as R goes to infinity. Okay. So the same. So that means what? That means there exists R0 such that this P of Z less than mu, greater than mu, if Z greater than R0. Okay, so the reason is just what this inequality shows, right? So this P of Z will become infinity, whatever direction you choose. Okay, so that means there exists R0 as some radius called R0 such that P of Z greater than mu if Z greater than R0. Okay. So that means what? That means let's fix this R0 and only consider this disk. Okay, and with the boundary. So which tell you that this disk is compact by this is closed and bound. So that there exists the point which you can pick this mu, right? Pick this mu because mu is an inf, right? So all the other points greater than R0 are already larger than mu. So the only possibilities that must be inside a disk or on the boundary. Okay, so there exists Z0 such that P of Z0, which is mu. Okay, so this is the most important step. Once you prove this, once you arrive this conclusion, then you already get an answer. Okay, so there is a Z0 such that P of Z0 absolute value is mu. So my claim is that mu must be 0. Okay, so if mu must be 0, then sure that I find the roots because PZ0 is 0. Okay, so the key idea is that you just try to find out the points which less than mu, right? And you prove by then you know that mu must be 0. Okay, so now consider QZ to be P of Z plus Z zeros divided by PZ0. Okay, so Q is non-constant polynomial by definition, right? Because polynomial, right? And Q of Z, okay, so let me just, I forget to write. So my claim is that mu is 0. If not, let's consider this Q of Z, right? Because P of Z0 is non-zero, so I can do the division. And I know that Q of 0 is just 1. Okay. And Q of Z absolute value will greater or equal to 1, right? For all Z. Right. The reason is that the P of Z0 is the by definition is the infiniment, right? So if you take absolute value, this Q of Z must greater or equal to 1. Okay, so there exists the integer k, smallest integer k, belongs to, let's say, 1n or 1 to n, such that your Q of Z is, let's say, 1 plus bk zk bn zn, such that bk is non-zero. Okay, because it is non-constant polynomial, so I can take the first non-zero term. Okay, and remember that by the previous theorem that I proved in the previous video, that there is a real number such that the exponential ik theta is negative bk. Okay, the reason is that I think this bk. So the reason is that any complex number with a modulo 1, then there exists a t which is real number such that the exponential it is z. Okay, so this is the very elementary because you just draw a circle and then you see, oh, where's the angle, right? So there it is the theta belongs to R such that bk times this become negative absolute bk. Okay, so now So now which tell you that 1 plus bk rk exponential I k theta. So remember that this guy is a negative bk, right? So if you take absolute value, this is just 1 minus rk bk. Okay, so this is valid if r greater than 0 and rk bk less than 1. Okay, so this must then take absolute value will make this guy positive. Okay, so let's consider q of r exponential I theta. Okay, so q of exponential I r theta is this, right? It's q of z is this. So the leading term will be, so this will less or equal to r1 minus rk, right? So zk, right? So the first term is bk absolute value minus r, bk plus 1, minus r n minus k, bn. Okay, so that means if you take r to be so if you take r to be very small, then all these terms will be dominated by this term, right? So you take r to be small enough, then your qr exponential I theta will definitely less than 1, right? Because all these terms can be arbitrarily small, and these terms will dominate, so you are less than 1. So contradiction, right? Because my assumption said the q of z is greater or equal to 1. Okay, so this is the then contract, right? So mu is 0, and then once mu is 0, then the your p of there you already proved that there is z0 such that 0. Okay, so all the key idea actually just come from here. This disk is compact. So then the infiniment and the suprema of the continuous function on a compact set can be achieved. Okay, so actually let me just write down the key step. The most key step is this. Let me just, so the continuous function on compact set can achieve its maximum, or basically in this case, since it can achieve, right? So maximum just suprema and infiniment. Okay, so so it's very interesting that seems like this is theorem called fundamental theorem of algebra, but none of the proof can be used top pure algebra. So there's a way that I just mentioned that you can use a Galois theory to prove fundamental theorem of algebra. But the problem is that you need a little bit of analysis. So somehow like the fundamental theorem of algebra cannot be proved purely by algebra. I think so. I think there's, yeah, maybe I will check. Yeah. Okay, so see you guys next video. Next video we talk about some basic Fourier analysis.